Hey, R fans, we are back. So now we're actually going to get into the running of this three-level model. In part one of this video, we talked about inputting data from other stat packages like Stata and how to work with variable labels and kind of pick apart what the labels mean and also do some cleaning and coding. So that is part one. So now we're here at part two. So you'll notice the nice part about R is that the flow of multi-level modeling really is the same whether you're doing a two-level model or a three-level model. So it's very versatile in that way. And the way you sort of proceed is pretty similar. So I'm going to walk through a typical analysis that you would do for a three-level model and help to make some sense of it. So just a reminder, we're using this data set, Project STAR, from the Tennessee class size experiment. We've got 6,000 kiddos, and we have 9 columns of variables that we're working with. There are a bunch of other variables we haven't considered, but this is just to get us started. And we have students. We're looking at their reading scale scores, so kindergartners' reading scores, nested within classroom and nested within school. So just like other types of multi-level models, the first thing you want to do is run a null model. So that's exactly the same, except in this case, we have a random intercept at the school level, and we have a random intercept at the classroom level. So in terms of the coding, I'm still going to call this thing, model 0 or model null, whatever you want to call it. And it's the same function, LMER. Read is my outcome, and then the tilde. And then I have, in this case, just 2 components. I have a random intercept at the school level, represented in exactly the same way as in a 2-level model, with a number 1 and then a pipe operator in the name of the cluster variable, school ID, plus, again, a second cluster variable for classroom ID. And then, of course, after that, I need to tell R where the data are. In this case, they're in this data frame called star.clean that I've already put together. So the coding is very similar. You're just adding another random component, and the random components go in parentheses, and that's really it. So that's a null model, a null 3-level model. So I'm going to run that and get a model summary here. Again, the top part is very similar to what we've seen before. I did want to show you, so if you notice, I did not do, there's an option here that I've been putting on the front, RMEL equals false, like that. And that's because by default, R uses what's called restricted maximum likelihood. And particularly when you have small samples, using restricted maximum likelihood is actually a pretty good idea. And so I just want to show you how to do that. You actually just take that option off. And by default, notice it says a linear mixed model fit by REML or REML, which is restricted maximum likelihood. In most cases, it doesn't make a big difference, to be honest. We're talking about hundredths of a point at most, but I did want to show you that. So in this case, we have a one fixed effect, which is our intercept, and that is 437.05. And if we had done some descriptive statistics on this data, which is always a good idea, that's probably pretty close to the mean score, a reading scale score in our data set. In this case, this would be the mean score after adjusting for students being nested within classrooms and also being nested within schools. And then we have, that's our only fixed effect because this is a null model. And then we have now 3 random effects because we have a 3-level model. So we have a random effect, random variance of the random effect at the student level, and that's equal to 728. We have a variance of the random effect at the school level, and that's equal to 169.8. And then we have a variance of the random effect at the classroom level, and that's equal to 115. All these look like they are likely to be pretty highly significant, just looking at the standard deviation, although we could always use the RAND function to get an LRT test, which we learned about last week and in previous weeks, to get a p-value for that comparison. So that's our null model. And of course, the most useful thing with a null model is getting an ICC. And in this case, we actually have 2 ICCs we need to calculate. And so I just put together a little function here to do this. And all you need to do is take your values and plug them in. So this is the level 2 ICC, which is the classroom. And in this case, I grabbed the classroom level variance, which is 115 or 114.9. And I divide that by the sum of all the variances. So 114.9 plus 169 plus 728. And then I ask R to print that value. So it's just a little arithmetic that adds together all those things. And we get a value of 0.11. So the ICC at the classroom level is 0.11. What does that mean? It means that 11% of the variability in reading scores is between classrooms within schools, because we have students nested within classrooms, nested within schools. So 11% of that variability is between classrooms in the same school. Kind of cool, kind of interesting. We also can calculate a level 3 ICC. So here we're just, instead of 114.9, we drop in 169.8, which is the school level variability. And we run that, and it's 0.17. So 17% of the variability is between schools. So 11% of the variability is between classrooms in the same school, and 17% of the variability is actually between schools. So that's really cool. You can start to think about where is the variability in scores, whatever you're looking at, and where's sort of the action, where's the most variability. In this case, we can do a little math. If we add 0.11 and 0.17, that gives us about 0.28. So 28% of the variability is not at the student level, right? That's what these are. So the student level would be 1 minus that, so that's like 0.72. So 72% of the variability is within classrooms between students. So there's still a ton of variability. Even in a typical classroom, you find a ton of variability in reading scores, even after accounting for the nesting of students within schools and within classrooms. So I don't know. I always think that's really fun to start to pull some of that stuff apart a little bit and look at how variability is actually happening. So that is a null 3-level model. So now let's proceed and start to add some predictors, because that's really what we're here to do. So first of all, what I recommend, just to keep yourself sane, I recommend adding predictors in chunks. So I would start with student level predictors, and then I would add level 2 predictors, and then I would add level 3 predictors. And then at the end of that, I would maybe play around with some random slopes if you have a big enough sample, or some cross-level interactions. And if you remember back to last week, that little flow diagram I showed you that came from the book by Hawks, that's a recommended approach for model building in a multi-level model. All we're doing is adding on a third level here where we're adding things in. So, okay, so model.1 is where I add my level 1 predictors. And in this case, I just have one, which is STU FRL. So this is whether or not a student qualifies for free and reduced lunch. And it goes right here in front of the random effects. And I should have said at the beginning, these can be in any order. So you don't have to put the level 2 before the level 3. R doesn't really care. It can separate those effects. You just have to list them both in any order. So here, all we've done is add in student FRL, and then we call it using the summary function. And again, I'm saving these because I'm going to put them in a summary at the end. That's always a good idea. So, okay, again, here are my random effects. Here's my equation, all that fun stuff. So here are my random effects. They look fairly similar, although my student level residual has gone down. It was 700 something. and now it's a bit lower at 600 something. So here are my fixed effects. First of all, I have two fixed effects. Before I only had one. So I have an intercept, and then I have an estimate for FRL. And because I specified this as a factor in the beginning, it's coded the way it should be, which means it's a mean comparison between groups. So this is the estimate for students who do not qualify for free lunch, and it's positive 15.61. And it's going to be significant. The t-value here is, the test statistic is 18, so that's going to be very significant. Remember, anything above 2 it's probably going to be statistically significant if you do an LRT. So what does that mean? Well, when you have just one categorical variable in a model, so the intercept is equal to the predicted test score or reading score for the reference category. And in this case, the reference category is the group that's not represented here. So here we have the estimate for non-free lunch kids. So this is the estimate for free lunch kids. So the predicted reading score for students who qualified for free lunch is about 428. And for non-free lunch kids, it's about 15 points higher. And it does look like that difference is statistically significant. Okay? So that's kind of how you interpret things. The intercept really gets kind of busy once you start to add variables in here, especially lots of categorical variables. So you'll see this intercept jump around quite a bit depending on what variables you've included in the model. Okay, so that's level 1. You can add more level 1 predictors. You can add interactions between level 1 predictors. All those things are possible and things we've talked about before. So now we specify another model, model.2, and now I'm going to add in some teacher level predictors. Remember, it's students nested within teachers nested within school, so these are level 2 predictors. I'm going to add in the years of experience teaching kindergarten for each teacher, and I'm going to add in class type, which is our kind of experimental variable. Remember, kids were assigned to either a small class, a regular class, or a regular class with a teacher's aide. And everything else stays the same. This is model.2. And I get my results here. We're getting more and more estimates. So again, here are my variance components. And of course, you could calculate effect sizes. Now we've learned that skill, right? So by going back to the null model, we could make this our target model, and we could calculate an effect size for this model if it ends up being our preferred model. It may not. But here I'm going to focus mostly on the fixed effects. So here's our intercept. It's slightly different. So we have an estimate for non-free lunch compared to free lunch, and that appears to be significant still, about 15 points. Years of experience are also significant, t-value of 2.5, and they're equal to 0.3. So what does that mean? Okay, so for each additional year of teaching experience that a teacher had, a child in that classroom would be predicted to score 0.3 points higher. So this is linear, so you can multiply that out. So compared to a teacher with 0 years experience, the same child in a classroom with a teacher with 10 years experience would be expected to score about 3 points higher on this reading assessment. So years of experience, at least in this data set, appear to really have an impact. And then we have our class type variables. And since there are 3 categories, we get 2 out of the 3. And of course, the reference category is captured in the intercept. So we get an estimate for regular class, and we get an estimate for regular plus a teacher's aide. So that means these are both in reference to the small class, which is our sort of experimental category. And we see both these estimates are negative, and they're both going to be statistically significant with t statistics below -3. So what does this mean? Okay, so a student in a regular class, regular size class, would be predicted to score about 6 points lower than the same student in a small class. So a difference of about 6 points. And a student in a regular class plus an aide would be expected to score about 5.3 points lower than a student in a small class. So notice both of these are in reference to a small class. So we can't say anything about the difference between regular class and regular plus an aide. Although, spoiler alert, the research found that there wasn't a difference between those two categories. There was a difference for small classes, but there was not a big difference for regular and regular plus a teacher's aide. So again, more categorical variables makes for more fun. And so technically, what does this intercept represent? This intercept represents the predicted score, reading score, for a free lunch student who has a teacher with 0 years experience and is in a small class. So that's the interpretation of the intercept. It's not all that important to be able to pull all those things out, but it is important to know all the components that are included in the intercept, especially when you have a lot of categorical variables. Okay, so that is level 2. So we've added a level 2 predictor. Now we're going to add a level 3 predictor. In this case, we're going to look at urbanicity. So does the geographic location of the school in terms of its census designation have an impact on the predicted test score? So this is model.3, and I'm going to add in urbanicity. So I've got FRL, years experience, type of class, and urbanicity. And this is going to be called model.3. So here we go. And notice our variance components are dropping a little bit. I'm looking here. I'm not going to calculate an effect size for this week, but keep in mind you can always do that with the tools we now have. So, okay, fixed effects. Wow, we're getting a really long list, aren't we? It's pretty, it's getting pretty intense. So, okay, so free lunch. Students with non-free lunch, that's still significant and still about 15 points, so that's pretty durable. Years of experience, still significant, 0.3. Regular class and aide are both significant and negative, so small class still seems to be doing pretty well. So now urbanicity. So we may want to look back to the top of our table here, of our code, to figure out which category is being left out. You can also use this table command that I did before, but I forgot that it wasn't converted to a factor yet. So I'm going to do table star.clean $, and urbanicity pops up right there, and hit enter. Aha, okay, so inner city is the reference. So that's the category that all these individual categories are being compared to. And in this case, we have a reference for schools that are in suburban areas, rural areas, and urban areas. All these estimates are positive, but they're not statistically significant. So notice those t-values are all less than 1. And in order to be statistically significant, the t-statistic would have to be above 2 or below -2. So these are not really close. So we're not seeing a big difference by urbanicity. Although keep in mind that's urbanicity while also controlling for free lunch status, years of experience, and class type. So, right, we could look at just urbanicity by itself if we kicked all these other variables out of the model. But in terms of the model we've run, we don't see a difference in urbanicity after controlling for the other variables that are in the model. Okay, so just a couple of the things I want to share with you. So sometimes I think it's cool to compare the same variable at all 3 levels. I think that can be really interesting. So in this case, we have student, teacher, and school level estimates of free and reduced lunch. So we have a variable that tells us whether or not the student qualifies for free and reduced lunch. Then we have a variable that tells us how many kids in the class qualify, and we have a variable that tells us how many kids in the school qualify. And we can include all 3 of those things simultaneously. So this is that getting at that levels piece. So you're really looking at the interplay between the different levels. In addition, we can also look at the other variables we've included before. So I just included class FRL and school FRL here to give us another angle on this. And as we look at the results, it's pretty interesting. So student free lunch, again, 15 points, very significant. So that hasn't changed. So students who don't qualify are expected to score about 15 points higher. The estimate for class FRL is about 2.6. The estimate for school FRL is about negative 2.13. Neither of those, though, is even close to statistically significant. So the t statistic here is less than 1, and here is less than negative 1. And so we don't see an impact. But if these were significant, so this would tell you that a 1-unit increase in class FRL would be associated with an increase of 2.6 points. So an increase here means more students who are not free lunch, because that's the way the variable was coded. Not free lunch was the higher value. And if this thing were significant, it would mean that an increase of 1 unit in school level FRL, so more students not qualifying for free lunch, would predict a decrease in scores. But again, that's also not statistically significant. But just to show you, you have the tools. If you measure something at the student level, it can be aggregated up to different levels to answer slightly different questions about the context in interesting ways. Okay, last model I'm going to show you is a model that includes a random slope. So this is a big data set. We've got 6,000 observations. We've got hundreds of schools. So this would be a data set where you could try some random slopes if you wanted to. So in this case, I'm going to go back to the previous model that worked pretty well. So FRL, years of experience, class type, and urbanicity. I might even drop urbanicity, but I'll leave it in for now. And let's say I wanted to test a random slope for years of experience. Now, here's the rule. This is an important thing to keep straight. So in the past, we could test a level 1 predictor as random at level 2. Okay, so in other words, a predictor at level 1 could be tested as random at level 2. A level 2 predictor can be tested as random if there is a level 3. So in this case, we have a level 3. So we can say, for example, does the impact of years of experience vary according to what school you're in? So this would be some kind of a question about teacher quality or teacher context. So does the number of years experience, that relationship between years of experience and reading score, does that vary according to what type of school you're in or what school you're in? And to do that, we just replace 1 in the school ID random effect statement with years of experience. So we've added testing a random slope for years of experience. We could also, for example, test a random slope for FRL at the classroom level. That's a level 1 predictor. We could test it as random at level 2. We could also test FRL as random at level 3. You can jump levels. So a level 1 predictor can also be tested as random at level 3. So you have a lot of options. Again, I recommend kind of choosing wisely here, not testing a bunch of these because they get pretty complicated and they rarely do improve the fit of the model, but it's worth testing 1 or 2. So we're going to try this random slope for years of experience. We get a little warning here. So remember, R is a little touchy, so we get sort of a convergence warning. This is a small convergence warning. So this usually means the solution isn't perfect. It's not exactly what we want, but it's not. It may not be a problem. In many cases, this is kind of a false warning, although it is definitely something you want to pay attention to, sort of note it as you look at it. So here in our random effects equation, everything else is pretty similar, but so here is our random effects equation, and notice at the school ID we now have an intercept, a random intercept at the school level, and then we have a random slope for years of experience. So that's that additional random term. So now we actually have 4 random terms. And we have a covariance between the intercept and years of experience at the school level. It's actually pretty high, actually, 0.56. That's kind of interesting. So that seems to be, could be kind of impactful. Now, to see whether or not we should use it, we can use a couple things. We can look at AIC and BIC, or it's often easier just to use the ANOVA command, which you use with a nested model, so comparing two nested models. So in this case, we're going to do an ANOVA between model 4, which did not include a random slope, and model 5, which did. And we'll get a likelihood ratio test with this. So here's model 4. It's really long, and model 5 is really long. So here we are, and model 4, model 5, the difference is about 6 chi-square points, and it's highly significant. I think we could also use the rand command. I think that'll give us pretty much the same information, and just put model.5. See if that gives us the same information. Oh, I need to say that's from Elmer test. So a little lazy loading there. Elmer test. Yes. Okay, so here is the same thing using random effects. So what this is doing is it's deleting single terms. So this is our original model. This is deleting class ID. So this is deleting the random slope for class ID. So this is definitely not a model improvement. And this is deleting the years of experience, what you call it, variable, the random slope here. And again, it's a LRT of 6.2. And it's equal to 0.04, so it's right on the borderline. We may want to include this, we may not. Just looking at the comparisons. So, if we're thinking about it, if it's a giant data set, yeah, we might include this random slope. It's pretty close. It's sort of right on the border there. So yeah, we do get fairly similar information. That LRT is still about 6 points. Doing that compared to the ANOVA. Okay. Of course, and then we can use the model summary and broom.mixed packages to organize our results. So this is the same setup as last week. So we have the model summary package and the broom.mixed package. And then we have models. So we need to create a list that holds all of our models. So we have 6 this week. We have model 0, 1, 2, 3, 4, and 5. And then we just call the model summary command on that list. And I just use the default output this time. You can use the R markdown if you want, or markdown. It's thinking. And then we get a nice model summary table. You also get this weird, so I'm not entirely sure why it wants to do this. But it gives you this huge, it gives you this like repeated standard deviation estimate. So what we need is, so this is a good estimate. This is the estimate for our intercept in models 1 through 6. And then really, let me pop this out into a separate window. So we can keep this. We can keep these first 2 lines. We actually just want to delete all of these. And there's a bunch of blank lines too. Again, this is R. It's free, so it's not always perfect right out of the bag. And then we want to keep here all the way down. So basically, we just need to delete all this stuff in the middle. But this is all good. So we get all of our class types and in all of our models 1 through 6. And again, you can always open this. I show you down here this last part. So you can create an HTML file, which I do here. So this saves an HTML file. And it's now right here, msum.html. And you can open that in Word, and then you can edit it just like a regular Word table. So that's what I recommend, is just to pull this thing into Word and work with it a little bit, because it's still a little clunky. Okay, so I think that's all I've got this week. So just to recap, we started with a null three-level model, very similar. We just added a second random component here for our level 2 and then our level 3. And then we talked about adding calculating an ICC at level 2 and at level 3, which we now have to do because we have 2 levels above the bottom. Then we added a level 1 predictor, we added a couple level 2 predictors, we added a level 3 predictor, and then we played around with adding the same predictor aggregated at different levels. And then finally we tried a random slope, and then we tested whether or not that random slope actually made a difference. So hopefully that makes sense, and I hope you have a good week.